In this presentation, we're going to go over our scissor jack design. Now here's the requirements. It has to lift 2,000 pounds, weigh less than 15 pounds, be cheap, rust resistant, and no maintenance required. Now for as our assumptions, we assume that everything's ductile and that there's no stress concentrations, meaning that those holes aren't going to be a source of cracking. All forces are in plane with the scissor jack, so there's no side to side, it's just in that plane with the jack. And all the forces are static, meaning that there's no inertial effects. And now to analyze this, we want to see where this thing could fail. We found that it could tear out, the holes could tear out in the frame, or double shear in the pin, buckling in the crossbar, bearing stress in the frame, or axial load in the crossbar as well. Now here's a little bit of force analysis versus crossbar length that we did in MATLAB. Here we plotted the forces that are applied on a frame member and also applied on the crossbar as a function of crossbar length. And we found that a suitable working range for the crossbar would be 4 to 13 inches. Here's some more plots in MATLAB. These show our stress versus crossbar length. And it shows, as you would expect, that as the crossbar length increases, that the stresses also increase. Except for in the bottom right graph where we show that as crossbar length increases, the critical load for buckling decreases, which is also what you would expect. Also, another important thing that we learned from these graphs is in the upper left, we find that the most problematic or worrisome part is the bearing stress in the frame, which is the red dashed line. For this reason, we chose to pay special attention to that area.
HB material selection criteria was employed to search for new materials. A design space of strength versus density was explored to find material for light and strong being, which is, in this case, are our frame members and crossbar. As shown in the graph on the right-hand side, material index and proposed constraints help to narrow down the selection of the material's upper left corner, which is high strength and low density area. Two cheaper available options in this case are aluminum and steel alloys. However, when we look at both the materials, steel is generally cheaper than aluminum, and that's why we select, and also it's stronger. So that's why we selected steel for further analysis. Here we changed the dimensions of our members. Here you can see the change in dimensions for the frame and crossbar. This was done to keep the geometry light while also accommodating all the loads that are being applied on the scissor jack. Here we compare the old and new design. This one is for frame, which is our primary area of concern. As you can see, after selecting the material and changing dimensions, the bearing stress is not really going to be a place for failure for the applied loads because the yield strength is much higher for the applied stresses. Then here we compare the buckling in the crossbar. After selecting the new material and also changing the geometry from square, hollow, cross-section to solid circle, we see that there is more, the critical load is higher, and also for the given length, the critical load is higher, which is a change in a couple of 100 pounds.
On this slide, we used ANSYS Mechanical to simulate tear-out failure in the frame. The boundary conditions that we used were a fixed support in blue and a force in red. This is simulating the actual forces in the frame during use. We used a 13-inch crossbar length in the calculations because that caused the greatest strain on the frame members. We used a force of 1,762 pounds acting on the outside diameter of the holes. The amount of force is found using hand calculations. As we can see from the results of this test, there's a predicted stress value of 36,953 and a hand calculated value of 37,694 PSI. The most stress, as we can see from the picture, will come from around the holes. The discrepancy between hand calculated values and predicted values could come from mesh sizing or distortion in the frame. The conclusions from our analysis are below. We found that the given procedure can be followed to design a scissor jack. We found that the material selection is elemental to the design process. We found that we could find a much stronger, lighter, cheaper frame using optimization. The cylindrical geometry that we chose for the crossbar was much less susceptible to buckling. We found that the newly proposed design can lift 2,000 pounds with a max safe applied load of 3,000 pounds, giving us a safety factor of 1.5. The total weight of the scissor jack is 4.2 pounds, which is well within our 15-pound design limit. Steel is much cheaper than aluminum. In our design, we found that we could in materials, we would spend about $4 compared to the $7 for the original design. And we found that the material could be painted to give us rust resistance.